So now we're going to look at the disk. This is the typo here. It should be electric potential. So let's see if we understand how we can get the potential for a disk using the equation from a ring. So we've already calculated the value for a ring. So for a ring, it's just equals to KE. Now, taking a disk, you can cut a small ring. So that's a small ring. And then you want to calculate how much amount of charge do you have in this small shell. And you're going to see that that charge is just going to be equal to 2 pi r times dr times my sigma. So sigma is equals to this amount of charge. So 2 pi radius dr is area, and then you want to multiply that by sigma, which is this equation right here. So that's the element of the area. Now let me show you exactly where. So let me stop my sharing here. Then I want to go back and share my. So let's look at this. Suppose I have this disk. This is the center of the disk. So it means that this is the radius. Now I'm looking at the disk from the top. So again, if this is my disk, I'm looking from the top here. So if you're looking at the top, what you're seeing is that you can cut a small shell. Let me use a different color here. So you're cutting a small shell. So the distance from here to here is small r. Now the thickness of the shell is dr. So it means that the area so this can be calculated as pi r plus dr squared minus pi. Does that make sense? So suppose I have two circles. One circle has a radius r plus dr, and one circle has a radius r. How would you calculate the area in between those two, right? Is the outer area minus the inner area. Do you guys agree with that? Now let's simplify this equation and see what we're going to get. So if you expand this is pi. So this is r squared plus 2r dr plus dr squared. Now, do you see that if you expand all of this, This pi r squared cancels with pi r squared, so this is equals to 2 pi r. It's pi dr squared. In calculus, we set that equals to 0. And what is the reason for setting that equals to 0? Because dr itself is very small, right? So if you take a number that is already too small and you square it, so just as an example, if dr was equal to some, let's say 0.01, which is 10 to the negative 2. Then dr squared would be 10 to the negative 4. So when you square a small number, it gets even smaller. So we just say that this contribution is very small and you focus on this. So your dA is 2 pi r, and then you're going to calculate your dq. So how much amount of charge do you have in that region? It's sigma times dA, and this would be sigma times 2 pi r. So that's what you're going to use when you calculate the electric field from a So basically, once you have this equation here, everything is done. So the calculation is already done. So as long as you get this, so what you're going to do now is that you take the value for a ring. So for a ring, we're going to say that V is equals to KE. So when you calculate the value for a disk, in place of Q, you replace that with dq. And then in place of X, so X becomes the new radius. So X is going to stay as X, but A becomes the radius, R, so lowercase r. And then you can just do the integral. So let me go back to let's go back to my PowerPoint here. So let me just, so this is what I was talking about here. So you can calculate your dq from here, which is this number. And then you use this value that we've already calculated for a ring. And then you want to run this integral from 0. So by going from 0 to r, it means that you want to cover so I need to sum all these areas from 0 up to the radius. So you end up with this integral right here. So now what they've done here is that they are trying to solve this integral, but again, remember that once you get to this point, you just need to go to your table and look up the value of, so you need to look up this integral here. So r over r squared plus x squared. And this is from 0 to r. So this is something that you look up from the table. You don't need to worry about trying to solve that integral. Just once you set up the integral, you just go to your table and look up the value. And if you do that carefully, you're going to get something that looks like this final value right here. And then we can also do the same, so we can calculate the x component of the electric field by taking the negative derivative of this value here. So for example, if V is equals to 2 pi KE sigma into square root of R squared, all of this minus X. So if you take the negative derivative of that, you should get this value right there. So I would say if you guys want to kind of like sit down very carefully and just review that. Now this is, I don't think I'm going to, you guys should remember this from the drill. So from the drill, again, you want to calculate the potential at this point. You just want to set up this integral here. So this is KE, the integral of the Q divided by R. So you can see that this is just equals to KE Q over L, integral from 0 to L. So your dq is just going to be equal to dx divided by x squared. And so remember that I'm substituting this value here as QL. And again, look this up. So you can see this from here. So this is your V. From here you can get your V. Now this integral here is given by this is the natural log. So if you substitute those values and you simplify, so again here just remember that the natural log of A minus the natural log of B is the same as the natural log of A over B. So that's how you get from here to here. So all of this is like A, and all of that is like B. So natural log of A minus natural log of B, you just divide the two.